This is similar to the last problem, but rather than the force being applied at 25 degrees above the horizontal, this is a push of a box at 400 newtons at 25 degrees below the horizontal. We have the same weight object. It is 1500 newtons. We have the same applied force is the one being pulled at 400 newtons at 25 degrees above the horizontal, and the same coefficient of friction. So here we're asked to find the normal force, the force of friction, and the net force, just as in the last problem. Now, if it wasn't obvious enough in the last video, what we're going to do here is break this force F that's 25 degrees below the horizontal into its vertical and horizontal components. Always do the vertical problem first. Now, if you notice, force F goes to the right, which is a positive horizontal force, and down. Okay, so it's going to be in the same direction as the gravitational pull. So here you see I've written the component of the force F, and that's simply going to be F sine theta. Gravitational force and the normal force are still in the same direction that I showed them on the last slide. Now, as with the last problem, this box is not accelerating up, it's not accelerating down, so I know that the net force in the y direction has to be equal to 0. Which means any forces going up, which is in this case only F sub n, have to be equal to the sum of all the forces going down, which in this case is the gravitational pull on the box or crate and the component of the applied force that is in the vertical direction. So the normal force here is going to be equal to 1500, which was the weight of the object, plus 400 sine 25, which is the vertical component of the push that is below the x-axis. This ends up giving us a normal force of 1669 newtons. And as I did last time, I decided to find the force of friction, of kinetic friction, by taking the coefficient of kinetic friction, mu sub k, and multiplying by the normal force. So that was given at 0.20, and we found the normal force in this case to be greater than the gravitational force, which makes sense because you're pushing down on it, and the frictional force ends up being 333.8 newtons. Okay, now the only forces in the horizontal direction are the frictional force, which we found to be 333.8 newtons. And this is the horizontal component of the applied force. This is 400 times the cosine of 25. Okay, so in this case, I can't say that the net force is 0. I don't know that. The only way I would know that is if I knew the acceleration were 0, which means it's either stationary or moving with a constant velocity. But I don't know that. So I write an equation that says the net force is equal to the force going to the right, which is F cosine theta, minus the frictional force, because that's going to the left. So when I solve that, I find that I have a net force of 28.7 newtons, and that is to the right. It is positive force, which means the acceleration of the object will be to the right.